Okay. Are you fascinated by crystals and gemstones and glasses and all this kind of stuff as well? Well, I am. Anyway, let's get into it. And also, we could discuss the question of, is an artificially created gemstone real? Is it good to use? Can you use it for metaphysical things? That's a question. In my experience, you can. It is slightly different, and we'll talk about that. So, we've got two major things, which is crystal and glass. And we can see here, it says a crystal or a crystalline solid is a solid material whose constituents, such as atoms or molecules, ions, etc., are arranged in a highly ordered microscopic structure, forming a crystal lattice that extends in all directions. So we can probably go crystal lattice. This is how, in an atomic kind of idea, that's how they do it, is that essentially the atoms are geometrical. Now, in a more realistic perspective, what that means is that you have these interesting geometry shapes. I don't know if it's going to give me one. Basically, it forms kind of cool geometrical shapes like that, physically. So when crystals grow, specifically if it is a solid that forms an organized structure, it has this cool geometrical look to it, right? Here we can see that this is using a model for, things like atoms and molecules and such. It's crystalline is organized, polycrystalline is kind of semi-organized, and amorphous is non-organized. Now, what is amorphous? Because if we understand that, then we understand the whole spectrum of crystals and glasses. So here we can see the page on amorphous solid. The etymology from Greek is without a shape, without a form. In condensed matter physics and material science, an amorphous solid, or a non-crystalline solid, is a solid that lacks the long-range order that is characteristic of crystals. So what it's saying, what does this mean, long-range order? Basically it's saying it lacks the order that a crystal has. The term glass and glassy solid is sometimes used synonymously with amorphous solids. Right, so here are some examples. Glasses, metallic stuff. So metal is like a gum or a resin. That's one important thing to realize. It's gummy and resinous. Glass is gummy and resinous as well, in a way. Plastic and polymers is also like a resin. You heat up plastic, it becomes a liquid, like a thick gelatinous kind of jelly-like liquid, and it hardens, and then it solidifies into this goopy looking thing, and of course you form it into a mold. Glass, metal and plastic are all like that, as well as resin, of course. For that matter, we could bring into bread dough or mashed potatoes or something, and it's also going to look like that. One of the most obvious examples of this is obsidian glass. Now, obsidian glass is formed by volcanoes, right? I believe, at least. I believe it's formed through volcanoes where they release all that magma, and then it solidifies, and you have this obsidian glass. It's a heat-based crystal. Here we go. Obsidian is a naturally occurring volcanic glass formed when lava extruded from a volcano cools rapidly with minimal crystal growth. It is an igneous rock or magmatic rock. I'll have to read about that one later on. So basically what it's saying, that magma pours out, and the magma chemically is, what is this stuff chemically? Consists of primarily silicon dioxide, 70% more. Silicon dioxide, an important one. Yeah, and then it would just be mineral stuff like impurities, which is basically just quartz glass, which quartz glass is very sharp, if you didn't know. So that's why it's so sharp. And it's just got impurities, which is how we can understand the coloring of crystals. So crystals are a base so a glass base or a crystal base, which gives it the form, which in this case is silicon dioxide, and then it is a coloring agent or an impurity agent. Because sometimes you have crystals which are halfway between like minerals and they're kind of crystals and kind of like ores and such, which usually it is the chemicals like an iron, a copper. You know, if you have blue crystals, it's like a malachite, or greeny blue crystals, it's copper, right? Or iron for jade as well. So this would be granite, here, rhyolite, whatever else kinds of things. Right, so when these things form slowly, usually they crystallize. This, you can see, it is not crystallized per se. It is a glass. And a glass and a crystallized crystal is very similar. In fact, it's essentially the same thing. It's just two spectrums of the same thing, right? So when you see your geometrical quartz crystal, which crystallized, meaning it has that like hexagonal, that geometrical shape. If we go to our quartz, it has this beautiful shape here that, you know, whether it was natural or unnatural, it crystallized. This glass kind of cooled like a resin. So we can see these are the two major kinds. We have glass and crystal. They're essentially the same thing. You can use them for mostly the same uses. There are going to be different uses, like there's a reason we use quartz for electronics and we don't use obsidian. Again, these are both silicon dioxide based crystals. If we go to composition, or well, technically, yeah, all right, here we go. A continuous framework of silicon 4 oxygens, right? Here we go. Silicon oxygen tetrahedra. It's a bit of a mouthful. I'm not enough of a chemist to understand how the different amounts of atoms affects the molecule and affects the actual product of it, but I do know that there are different forms of, just say like copper oxide. You've got different copper oxides, like oxide 2, oxide 3, oxide probably 4, and this affects the color and qualities of it. So I something to do with that. Well, there's something there. That's beyond the point. It doesn't really matter. So here again, just to reiterate, we'll get into the creation, some other things a little in a minute, but just for now. Again, glass and crystal, the two major things. Now, two main crystals that we want to look at is firstly quartz, which again, silicon dioxide. And to brush up on your chemistry, the oxide, usually when you attach an oxide to a metal or a metalloid, I think silicon's a metalloid, or it's like a transition or something, I don't know, some kind of, you can make it into a metal, but it's a bit of a peculiar substance. The oxide is usually when you heat things in air in the presence of oxygen. When you heat it, you cook it, you bake it, it oxidizes. And if you have like metal powder and you just heat it on a stove, on a plate, it'll oxidize, right? That's how you do it, that's how you get it. One way. Otherwise, because you've got to understand the composition of clay, this is very important, the chemical composition of clay. This is at least kaolinite, which I believe is like China clay that they used to make porcelain, but it's pretty much, it's all various, it's all similar. It's aluminium, this one specifically is aluminium 2, silicon, this one again, silicon 2, oxygen, so it's an aluminium silicon oxide type material, and OH4. I don't completely understand what the OH4 is. The I guess it's some form of hydroxide. So it's like an oxide, but also hydroxide. I'm not completely sure. Look, point being, sand is silica. Clay is aluminium, silicon, ceramic. I call ceramics oxides, hydroxides, carbonates, dirt, mineral, earthly type things, right? Simple. Most of the earth is that dirt is just clay and sand and dead organic material, basically like fermented material of organics, you know, leaves, animals, crap, whatever. That's most of the world. If we go to this abundance of elements in Earth's crust, number one is oxygen, 46%. Wouldn't you think like, hey, isn't that, you know, you got a lot of oxygen in the air. Technically, we've got a lot of nitrogen. Was it like 70%? Then we got like 15, 16% oxygen. How is there so much oxygen in the ground? And then we got silicon, the thing that we use to make silicon rubber, silicon like a gels and lubricants, silicon wafers and the computer chips, silicon ceramic, silicon metal. You can make fireworks out of it. Like what? Nearly 30% of the Earth is silicon-based materials, right? And then it's 8% aluminium, 5% iron. Iron, of course, there's a lot of iron in the clay. There's a lot of iron rocks. But the point I'm trying to get into your head is that underground, if you start digging stuff, dirt, it's probably some kind of silicon, aluminium, oxide type material, and also iron impurities depending on where you live. Also, if you want to look at it, calcium, sodium, magnesium, potassium, minerals, these also are in certain minerals, and in certain, there's calcite and lime deposits and whatever, so we can go into those another time, but just look at the main three. Then when you have the cycle of elements, as I said, if you heat things up in open air, you get the oxide. If you have rain come down, then the sun, and then it evaporate, and the rain come down, and day and night, and winter, summer, all of these cycles of the elements, you're eventually evaporating, and eventually consolidating and condensing, and then evaporating, and all these things. You're essentially creating this layer of topsoil full of, the oxides and such. Something to do with that, right? And underground, we know that there's, heat, moisture, minerals, as in like electrolyte minerals, right? Calcium, sodium, magnesium, potassium, sulfur, phosphorus, fluorine, etc., chlorine. You've got heat channels, you've got magma. So again, as we said, the glasses are made from superheating things. Crystals are made from usually slower, I don't fully understand them, but slower condensing of something. These crystals, you can see there, they condensed somehow. These are calcite, somehow they've condensed, and because it's slow, because it's not like you're putting a bunch of sugar in a pan and you're just heating it, gelatinizing it into like a toffee. But if you did it slower, maybe like you put sugar in water and you evaporated the water, you'd crystallize it out. So there's these two different methods, and again, as I said, you need a base. Silicon dioxide, base number one. Aluminium oxide, base number two. This is called alumina, right? It's used in, if we can see, maybe it'll talk about, here we go, armor. It's used in grinding discs. If you know what, like metal grinding discs, because this stuff is incredibly abrasive. It's got a 9 on the Mohs hardness scale. I don't know if it'll say it here, but it's very, very abrasive, very, very hard stuff. And what aluminium oxide forms, the same way that silicon dioxide forms quartz, if you heat this stuff, you get quartz glass. If you heat this stuff, you get a corundum. It's called corundum. That's the gemstone. And here we go. This is the crystalline form. So the crystalline corundum is natural. So if you have this is ruby and sapphire. Emerald's a different gem, I think. I think amethyst is a corundum. I don't remember. We can see here crystal, it's a model. It's not real, it's a model. Remember, don't confuse the models with reality, but it's at least this is what a scientist thinks it is, or maybe they've looked under a microscope. If you look under a microscope, you see the geometrical patterns, but at the end of the day, it's not as clean and as perfect and as nice and as, nature's a little dirty. It's a little imperfect, but we can make things perfect on a computer or in a lab like this. So don't get distracted by the models. The corundum is the crystalline form of aluminum oxide, 2 aluminiums, 3 of the oxygen. So under the earth, it's forming these crystals using the clay, probably some kind of mineral. Maybe it's not clay. Maybe clay forms into another mineral. This is what the alchemist would say. One mineral forms into another mineral forms into another mineral. I think it was like malachite forms into pyrite, and that forms into malachite or something. I don't know. They have this, and eventually it forms into gold. Whether that's true or not, I'm not sure. You can go into the Golden Chain of Homer to look that one up. Going on, so ruby, sapphire, rubies are lovely, aren't they? Sapphires are lovely. We can see here this nice big chunk of glassy, kind of icy, like looks like red ice. Looks like someone made like raspberry ice cubes. That'd be tasty. And here is some naturally occurring crystal, and you can see this one, because it's natural, it's a little less glassy. When I say glassy, I mean that's a pure piece. Now, either that's an incredibly expensive piece of ruby, because the price of a gem is, firstly, is it cut? Like, is it carved into a nice little shape and all that? Like this one, I think it's got a... I don't know if the back is carved, or I think the front is carved as well, actually. And then secondly, how glassy is it? How clear is it? Clearness. You see, this one is clear. That's not clear. If you cut that one up, it's not going to look like that. If you cut this one up, it's not going to look that perfect. You can get it looking pretty nice, but it's not quite as clear, right? Which is why when you heat your crystal material, your glass material up to make a glass, assuming you don't get any impurities in it, it's a lot clearer. Synthetics, there we go. This guy Gordon made the first synthetic rubies by fusing potash, alum, or potassium alum, which is potassium, aluminium. Here we go with the sulfur, oxygen 4. You buy it pretty easily at a high temperature with a little chromium. Chromium is a pigment of rubies, by the way. Okay, so we just basically mixed alum and chromium and heat them up. Yeah, this stuff, you call it alum, they use it for like shaving blocks, mineral shaving blocks. It's made of alum. Then this person made white sapphires by fusing alumina in boric acid. So assumably the sapphire doesn't need a boron to color it. If we go to, here we go. Okay, there's a lot of impurities with tracing elements such as iron, titanium, cobalt, lead, chromium, vanadium, magnesium, boron, and silicon. Because there are a lot of different colors of sapphire. Isn't that a lovely looking stone? Yellow sapphire, blue sapphire, pink sapphire. Can you see these? Yes, you can. Red sapphire, star sapphire. All these different kinds of sapphire. So, and then you can look at like what makes a sapphire different from a ruby, and there's probably some kind of specific thing based on its geometrical shape or something. I don't know. I really don't understand that, because again, at the end of the day, it's aluminum or aluminium 2. It's this alpha. Here we go. Alpha aluminum 2, 3 oxygen. While the ruby is just says corundum. Aluminum 2, oxide 3. Okay. Again, we're getting a little too specific. You don't have to worry too much about this. It's a bit like there's nothing wrong with you just taking quartz and using, or silicon dioxide, which is just crushed up quartz glass. You get a bunch of jars, you crush them up. There's going to be impurities in them, but who cares? There's nothing wrong with you doing that and making gemstones out of it. Like a diamond. What's a diamond? A solid form of the element carbon with its atoms arranged in crystalline structure called a diamond cubic. Interesting. So diamond's kind of Saturnian in that way. So specifically the seed or the material, like the mother material, the earth, the body of the diamond is carbon. It's just in and arranged in a geometrical pattern. Now, diamond's a little bit of a weird, kind of confusing one. I don't fully understand it, so I'm not going to talk about it. But you can probably research that yourself, right? What really is like the diamond looks pretty much the same as quartz, doesn't it? I don't know. Maybe on a ring. Doesn't. Point being, there's nothing wrong with making quartz crystals, right? Is what I'm trying to say. So again, there are all kinds of different kinds of quartz, right? Jade is the word the Chinese would use for different minerals, right? Specifically nephrite. I think nephrite was the ancient Chinese jade. But it's a bit of a complicated history. I'm not exactly sure. Specifically nephrite, it says it's a silicate. Is that? Yeah, here we go. It's a silicate. Oh no, here we go. Yep. So calcium, magnesium and iron are like the impurities, I think, and then it's like a calcium, silicon, oxygen, and then hydroxide. You got that as well. So it's a bit of a complicated mineral. Is what we could say. Jadeite is more of a, here we go, sodium, aluminium, silicon, oxygen. Okay, so it is a silicon oxygen. It's like a quartz. It's like a more of a complicated quartz. You can think a more complicated quartz, right? So these things, they're all very similar. Alright, so here's an old video that you can check out yourself, which is talking about synthetic quartz using specifically the pressure method. So you see they've got these giant vats, and he's going to pull this up, right? And you can see the steam coming out. So it's, I think it's a pressurized, I don't know if it's underwater. It's probably hot water hydroxide. You see these giant chunks. Let me back that up. Look at that. Giant chunks of quartz, and this is like crystal. It's in a geometrical shape, you can see. I think at least. I think if you looked at that under a microscope, it would be geometrical. And this is what they use for like factory stuff. And it's pressurized, like tanks of, I think, hydroxide or lye, some kind of lye, like potassium, sodium hydroxide, and it's underwater. This is a little more advanced. You look at that, and it just goes deep underground. It's a little more advanced than what maybe you could do in a lab, but I don't know. Maybe you could do it in a flask or something. I still, I'd like to look at that. And what they use is an actual piece of quartz as like the seed, the holder, and then the quartz grows around it, because they put a bunch of like impure quartz crystals in the liquid, and with the high temperature, high pressure, and the hydroxide, it dissolves it supposedly. This is probably what's going on underground, where you've got like literal currents, like currents of quartz liquid. And that's how like trees, you've got certain trees that like become an opal, or like become a crystal. Is that I think there's like a current of quartz liquid, right? And again, that would be because you've got to think the clay and the dirt and the rocks and all this stuff, the higher form of that is the glass of the crystal. That's just a more refined version of it, right? Yeah, here we go. Seed crystal, natural quartz, and you've got this vat of water. I don't know if I can show this guy's video because it's, you know, I don't know. But look, go watch it. How to make synthetic ruby in the workshop. Essentially, he's got that crucible there. There, we can see it in the thing. That's an electrode, and it's electrically like zapping the crucible and heating up the powder in there, which is the corundum powder, with the the chromium and corundum being the alumina or aluminum oxide, and then you basically just make a ruby glass, and you can see it looks resinous and glassy, right? This one's just showing someone like grinding a rock into a gemstone. You know, that's kind of how they polish it, right? They grind it. Now here's an interesting one. We have making salt crystals, and salt is salt you can think of, you know, is kind of like an element, so like a metal or metalloid or some kind of, you know, thing. It can even be you know, like citric acid, I guess, is a crystal. So it can be an organic thing, and then you've usually got something else attached to it, like the chlorine or the fluorine or the... Right, so, and it's in a crystalline form. Salt is in a crystalline form, right? And what they're doing is they're dissolving the salt in water, and usually you should be able to dissolve the salt in water, right? Adding coloring, whatever. And they're doing this little string method, which usually people do in like a science class, or if they've got kids or whatever, or they just want to practice. And the crystals will grow in this because it's super saturated. Now specifically, this is more of a salt. We're going to understand the difference between the salt. The difference between the salt, here we go, see sodium and the chlorine, the two different things. Because it looks, you know, it looks like it's a crystal or a glass or something. It looks similar enough, right? But the difference is that this is dissolved in water. Your sapphire is not dissolved in water. You can crush the sapphire up. It's still not going to be dissolved in water. You can burn it. I mean, if you burn it enough, it's eventually just going to turn into minerals again, because you're going to release the oxygen and or well, some of the oxygen, and then just turn it into an oxide, right? For whatever its elements are, right? So, but you can use the salt as a coloring agent, the same way we have the sapphire and we have the ruby. The amethyst, what's the structure of this fella? Impurities of iron. Anyway, so it's a quartz with iron impurities. Radiation, interesting. Okay, right. So the iron, you would take a salt of iron. I don't know which one specifically. You could just randomly, you know, iron sulfate, iron chloride, iron whatever you can get, or even just iron powder. But it's, you know, it's kind of nice to use as salt, I guess. It's kind of easier. And then you get your quartz, your crushed up quartz, your silicon dioxide, and you heat them together, or you use the water methods, which again I don't know a good enough method to tell you besides just heating things up, you know, via electrolysis, microwave, or gas torch or gas furnace or electric furnace. Besides that, I don't know the crystallization method, so to speak, of you know, is there a way we can dissolve quartz and then crystallize it? You know, the idea of like in nature how the quartz dissolves into water. How does it do that? Does it use a certain chemical? Because if we can figure that out, we can, you know, make crystals, right? Instead of just glasses. Do you use a chemical? Is it just pressure and heat? I don't know. I'm going to have to research that after this video. At least now, you should have a basic fundamental idea of crystals. And you should probably understand that you can see a natural crystal is usually just an impure one. As I said, with that ruby, the glass is more clear. The valuable ones is more clear, right? The expensive ones is clear. The impure ones are more earthly. You see, this amethyst is on like a piece of mineral. It's grown from this piece of mineral, so to speak. assumably. It's like it's the parent of it, like the support, the foundation of it, and then the crystal is just the refinement, the kind of coming off of that, right? Artificial one is usually we're just trying to make that nice, clear, glassy looking stuff. But you can also, and again, you can make it either a glass or a crystal, which means it's structured or unstructured, geometric or just resinous. It's up to you. You can even make it like mineralish if you want, if you figure out how to make that. But that's more like geopolymer, which maybe I'll do another video on, which is literally just basically cementing, you know, just like calcium oxides and sand and different rocks, and you know, like making fake marble and fake whatever. Because that's what, you know, mortar and cement and concrete and technically cement is powder, but and then concrete is when you mix it with rocks, I think, and mortar is you use with bricks, and then you've got plaster, which is pretty much just mortar, but you apply it over a house, right, or over something. Just geopolymer. It's going to be another video maybe. Look, you get the point. Either way, I will do this and I will show you all this stuff, like making it, once I get the materials and once I get the tools and the time. It, you know, it could be, you could be waiting a while, so just, you know, it'll come, but just know that I can't do it right now. Probably not. Anyway, hope you enjoyed. Of course, check the links in the description, social, commercial stuff, and have a nice day.